Welcome to Fun with Science, Technology, and Engineering. My name is Mr. Ross. Today we're going to be doing some experiments with sound, and my acoustical engineers this morning are
Caitlin and Melissa.
Caitlin and Melissa. What is sound anyway? Do you know?
Something that we hear.
Something that you hear. I'm all the way over here talking. How does it get into your ears?
Sound waves.
Sound waves, right? And what are sound waves?
They hit our eardrums so we can hear it.
They hit your eardrums and you can hear it. But what are they?
I don't know. What are they?
What are you don't know. What are they? Right. What is happening when my voice, when my vocal cords vibrate back and forth? It causes the air to compress, like we had compression in bridges, and then it expands, and it compresses and expands. All right. And when it compresses, the pressure goes up a little bit, and when it expands, the pressure goes down a little bit. When it compresses, pressure goes up, expands, pressure goes down. So, what is happening is that wave. The air is not moving, is it? You don't feel any wind when I talk to you,
no.
Right? But those compression waves and expansion come along, and they cause the pressure on your eardrum to change a little bit, right? And that changing of pressure in the eardrum moves those little bones in there, right, which stimulates the nerves and says, aha, this guy is talking to me, and he's saying your brain unscrambles it all and says, you know, whatever I'm saying. Or if I sing, which you don't want me to do, right?
Oh, come on.
No. We're going to sing. So, sound waves are actually vibrations in the air, right? They're compression of the air and expansion of the air. Right now, how come we sound a little bit different? You sound one way, you sound another way.
Because we had
I sound differently.
voices.
And when we listen to ourselves on the TV, we're going to sound a little bit different yet, right? Not like what we're sounding, right? Why is that?
I don't know. Why is that?
You don't know why is that? All right. Well, the reason for it is because sound, not only does it have, you know, goes through by waves, but it also has amplitude, right, which is the amount of energy. If I talk real soft like this, right, there's not much energy. If I talk real loud, right, there's more energy coming into your ear, and that's called amplitude, the amplitude of the sound, right? But it also has some frequency, which is how many compressions and expansions you get per second coming past your ear. So if I talk like this, right, real high frequency, right, that's a high frequency, high pitch. If I talk like this, right, that's a low frequency and low pitch, right? You're laughing at me again, right? You shouldn't be doing that. Right, so now, so we've got amount of energy, which is the loudness coming into you, right? Now, do you think my voice is coming right straight to you?
No.
No.
How is it getting there?
Why is it? How is it getting there?
All right. Some of it is coming straight on. Some of it is bouncing off the wall, coming to you. Some of it's bouncing off the ceiling, coming down to you. Some of it's bouncing off the floor. Some of it's bouncing off of this wall back here. Some of it's bouncing off our head, right? So what you hear is sound coming from all different directions, right? I would sound much different to you probably if the sound came right straight in to you, right, and didn't bounce off all these things. So that is one of the reasons I sound a little bit different than you sound. Also, the frequency of my voice, right? My voice is not one single frequency; it's a whole bunch of frequencies, right? And which makes up the character of my voice. My voice sounds a little bit deeper than yours, right, because you have a different set of frequencies making up your voice. You have a different set making up your voice. And the amplitude of each one of those, it's not a single sound that you're getting, but you're getting you're making a complex sound whenever you talk or whenever you play a musical instrument. Right? And that makes up the different characteristics. Like if you were to play a note on the piano, play a note on the guitar, play a note on the flute, same note, they just all sound the same? No, because when you hit the key on the piano, what it does is strikes a string, right? And that string does not put out one single frequency, it puts out several frequencies, which gives it the characteristic. It makes it sound like a piano. Pluck a string on a guitar, makes it sound like a guitar, right? Because of the different frequencies. So, now, why do you think when you record your voice on, let's say, a tape recorder, right, and listen to it, you sound funny?
I don't know.
You don't know why? You don't know why you sound funny? It's your voice. What do you think? Do you have an idea?
No.
All right, what I want you to do, I want you to put your fingers in your ears, close your eyes, stick out your tongue. Okay, that doesn't have anything to do with sound. All right, but I thought it was funny. Now what I want you to do, is I want you to put your fingers in your ear, and I want you to talk. You talk.
Hello?
You sound different?
Yeah.
You can
Yeah.
still hear yourself, right?
Yep.
Say something.
Hello.
Hello? Is that all you can say? Say some more.
What's going on?
What's going on? All right, so now then, take your fingers out. Do you sound different when you put your fingers in your ears? What
Yeah.
What happens to your voice?
It goes, fades, kind of.
It fades down a little bit. Is it as high a pitched as what you hear when you're here talking?
No.
It's a lower pitch, right? The reason is because what you get into your ears, right, is the sound of your voice bouncing off of all these things, right, coming into your ear, stimulating your eardrum. You also get sound from your vocal cords, right, up through your head, through the bones in your head, into your ear. Right? So when you put your fingers in here, you're blocking out all the sound coming from everywhere else, right? And what you're hearing is the sound coming through here, right? And it's usually a little bit lower frequency, right? So you sound like a lower pitch, right? To the sound coming through the bones in your head, right? So that's why whenever you take and you record your voice on a little tape recorder, right? Of course, the tape recorder can't hear what's coming through the bones in your head, right? All it hears is what's coming out of your mouth, right? So when you play it back, you look at it and say, ah, or listen to it and say, ah, I sound funny. Okay. So let's do a couple things. Let's see if we can demonstrate how sound waves travel, right? Down here I have a giant slinky. Right? Right, this is Slinky. Everybody plays with Slinkies, right?
Slinky.
No. What do we say sound waves were? Sound waves travel through the air, and what they do is they compress and they expand. They compress and they expand. So what I want you to do, one of you, hold this up a little bit, stretch it out just a wee bit more. All right, now then, what I want you to do is to squeeze several,
More?
yeah, like that, and let go of it. So let's see what happens. What happened to it?
Went back and forth and back.
It went back and forth, right? Let's try it again. We have all the air compressed right there, and you're going to let go of it, and the spring is not going to move, right? But what's going to happen? Go ahead. It goes back and forth, right? It goes down, hits her hand.
Goes back.
She feels. Did you feel the energy when it came down? Try it again. Let's see. Wake her up with the energy. Can you feel that energy hit your hand?
Yeah.
I can feel
Let
it.
go of it. Did we let go of it? Right, so you can feel it. So that's in essence the same way the sound energy is traveling through the air. It's squeezing it together and coming to hit your eardrums and stimulate those bones, which in turn stimulates the nerves. All right, so. Okay. Now, if we were able to, of course, mechanically we can't do it, but if we were able to do that fast enough, right, we could get our different sound frequencies. Now, what I want you to do is I want you to squeeze your ear together like this. I want you to squeeze your ear together like this, all right? Get some more. Be powerful there, right? Now, when I say go, I want both of you to let go of it and watch very carefully what happens.
Okay.
No. Here, hold this end right here. Hold it right there. Okay, and squeeze this together like this. So don't let go of that end. Okay, just let go of this end. All right, go. What happened?
They went.
They went to the middle and
Then came back.
They went to the middle and
came
came back.
back.
Right, but you think they just try it again?
Ready? Set. Go.
go.
Yours went this way, hit her, went
And-
back. Hers passed it and went this way, right? Same thing. If you and I talk at the same time,
Yeah.
all right, my sound waves are coming to you, all right, your sound waves are coming to me, right, and they pass each other, right? They don't interfere with one another necessarily, but they pass each other, right? Let's try it again.
do a big one. 1, 2, 3,
Three.
go.
All right? So, now, that's what's called a longitudinal wave, right? The wave is traveling in the same direction, right, along the axis, the same way as it's moving. This wave is moving like this, right? So that's a longitudinal wave. That's what sound waves are, right? They're longitudinal waves. They're compression, and they compress and expand in the direction in which they're moving, right? Which in most cases are in all directions. But anyway, so now then, what I want you to do, I want you to hold your end very steady, right? And I want you to move your end up and down real quick, right? Right, this is another kind of wave. This is called a transverse wave, right? Now, sound waves don't travel like this, but some of the other waves do, right? It's the transverse wave. Faster. Faster, faster. Hold your end steady. Faster, 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 faster. And if you hit me, you're going to kill me. Go ahead. Faster, faster. All right, let me come around and let me show you. A second. Like that.
Okay.
All right? You don't have to go up and down too far. Just. All right, now, we have, keep it, don't stop. All right, keep it up. All right, what we have is this is called a transverse wave. And if you notice, there's a peak here, and there's a peak over here, right? Keep going. Quicker.
Oh,
Right.
you want to? Okay.
Right. We got 2 peaks, right? And that distance between those 2 peaks, or the distance between the 2 spots, same spots on the wave, is called wavelength, how long it is, right? In this case, it looks to be like about a meter long, right? And in the middle here, we have a little node. Keep going. So now, is the spring actually moving back and forth? It's not, right? But the energy
No.
is traveling in that wave motion
Your turn.
through the spring. All right, you look like you're getting tired, so why don't we put it down for just a moment, okay? Let's try this. What's this?
A string.
A
String.
piece of string, right? What's a guitar have on it?
Strings.
String. Okay. And what am I doing? Let's go back to bridges again. Now then, what am I doing? Putting.
Pulling it.
Pulling.
I'm pulling it,
Put
but we
pressure
call it.
on.
What was the word? Started with a T.
Torsion.
Torsion.
Torsion was twisting. This is this is tension.
Tension.
Tension. All right. So what I'm doing is I'm putting a little tension on this piece of string, right? And if I take this piece of string and I some tension, what's
noise.
happening? I've got a sound,
Vibrate.
right? It vibrates, right? Vibrates is sort of like that spring that we had down there. We're working. It vibrates down. Now, if I put some more tension on it, what happened?
It goes more, it makes more sound.
All right, it made more sound because I'm flicking it maybe a little bit harder. But what happens to the frequency? What happens to the pitch? Can you hear the pitch?
It's going faster.
A little bit.
Okay, what happens to it?
Now it's getting louder.
Okay, if I don't put so much tension on it, listen to the pitch. It's pretty low, right? It's talking
Yeah.
down here real low. Now if I squeeze it, put tension on it,
Then you can hear it really well.
but what happens to it? It goes,
It goes higher.
it goes higher, right? It goes higher in pitch or higher in frequency. Right, so that's what happens on a guitar string, okay? When they adjust the guitar, right?
They can put it tighter or
They
looser.
put it tighter or looser, and the tighter they put it, the higher the pitch, the higher the frequency, the higher the number of cycles per second that happens. Okay? Less tension, the lower the pitch. So, and what is causing that? What's causing the sound?
Tension.
Tension is what's causing the sound.
You're flickering.
It's
it.
vibrating.
I'm flickering, but what's happening?
It's vibrating.
It's vibrating, right? Just like my vocal cords are vibrating, all right? And then when it vibrates up and down, what's happening? It's causing the air to compress and expand, right? Which makes that sound wave coming through to your ear over here, and maybe to the microphone, right? So, same thing. What if it's vibrated?
Then it would be really loud.
Hmm?
I think it would be really loud.
You think it'd be really
yeah,
loud?
It will be loud.
Yeah. Loud enough.
You can
It
hear.
don't vibrate.
Hmm?
Yeah, you can hear it vibrate.
Or you can hear the sound waves going through.
What's the
Like
difference?
an echo.
What's the difference between here?
It gets louder as you go down it.
Yeah.
Every time you move your hand, it gets louder.
Every time. So, what's that tell me?
There's more room for the sound waves to go through.
All right. You notice when we did the slinky and it was going up and down, up and down, up and down,
Yeah.
and there was a spot in it where it didn't really move up and down, it stayed still. All right. The same thing when I take this and I hit this thing and it starts to vibrate. All right. Depending on how long it is, there's going to be spots on it, and it's actually vibrating up and down just like that slinky to make the sound. All right. But there are spots that aren't moving. Right. And if I hold it in some spot where it wants to move and I hit it, it doesn't ring. Right. It's just clunk, clunk. Right. Just like clunk, clunk. All right. So now, if I take and I hold it here, right, and I've got you. I cheated because I have it marked, the little marker. Right? I know that that's a spot that when this thing starts to vibrate up and down this way, or back and forth as I hold it up, right, this spot's going to stay still. So I can hold it right there. Right? And listen to it ring. Go down a little bit further, I can get another spot. Hear it ring? But if I go right in between here, it goes clunk, clunk. It doesn't ring like that. Hear it ring? If I come up here, it doesn't ring as much, right?
No, right.
Clunk, clunk, no ring. If I go down this little bit,
Rings.
it rings, right? So, and the pitch is different, right? The frequency, the number of times that it vibrates back and forth is going to be different. Right down here, it's pretty high. If I'm up here, it's a little bit lower, right? If you can listen to it, and your ear can detect the difference in the pitch. It's a little bit lower up here because this is longer, right, than it is when I go down. Same idea with, what's this?
A xylophone.
It's a xylophone. And look at it, how it's built, right? We got a piece of tubing.
It goes from smaller to bigger.
Right, but look at this piece of tubing we got here. Right, well, yeah, this goes smaller to bigger, but look at this piece of tubing. What happens? Right, they got a little hole through here, a little hole through here, and they got a piece of string to hold it. Where do you think those strings are?
Where the point that makes it ring, like
That point where it makes it ring. The point it's not going to move, right? Like, if I were going to make this into a xylophone, what I would do is I'd drill a hole right there, and I come down on this end, and I drill a hole the same distance, right? And I would make it whatever xylophone. Now then, these are all different sizes, right? We got little ones down here, and we got bigger ones up here. Why?
because
They make
like,
different noises.
makes different noises.
Makes different noises, makes different sounds.
Yeah.
This is a musical instrument. It does not make noise, all right? We have different sounds. Now, what do you think about the frequencies, the pitch on this one and this one?
I think one's higher and one's lower.
One's higher and one's lower. Which one do you think is high and which one do you think is low?
The big one's
I think
high.
the bigger one's high and this one.
You think the bigger one's high? Let's see. You got that one? All right.
Yeah.
Which is low?
The bigger. That one's more. The bigger one's lower.
The
Yeah.
bigger one's lower. So these ones in between, if this one is a little bit longer than this, right? So this is going to be what? As we go down this way, this is going to be real low. This is going to be a little bit higher, 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 a little bit, and this will be the highest one. So we want to try it?
Sure.
Give me a real high pitched note.
No, high.
Yeah, that one down there. Give me one in the middle. That was pretty flat. Okay, that's all right. What about this one? All right, so this is the low, that's the high end, high different frequencies. Right, so how does the sound get from me to you?
Sound waves.
And it bounces
Sound
off
waves.
things.
And it bounces
Bounces off
off
the
things,
wall.
right? It doesn't come straight to you, it bounces off the wall, the ceiling, floors, and all that sort of thing. So when you go into a theater, right,
The noise is bouncing off the
but
walls.
what they have to do when they design that theater is they have to design it so that when the sound waves all bounce off the wall, they come to you, right, in some sort of fidelity kind of a thing. And you said you can, if there's an orchestra playing, you can hear the orchestra. In fact, not too long ago, I met a young engineer. He had the ideal job. He was an acoustical engineer, right? You know what his job was? He worked for one of the manufacturers of audio equipment. His job, they paid him for this, believe it or not, is to go to concerts
Oh,
and listen to the music. And obviously, he had a very good ear for sound, right? So they pay him for that. And then after he went to the concert, he would come back, and his main job was this company had all kinds of little laboratories set up where they tested their equipment, right? And they have different rooms set up like it's a living room, a den, whatever, right? And he would go in and sit down, and I don't know whether they give him anything to eat, munch on or not, but he would sit and listen to the audio equipment and let them know if it sounded like the live concert. That was his job. They paid him several $1,000s a year for doing this. And you just, hey. So I want one of those jobs when I grow up. So now, one other little experiment we can talk about is I have a tin can with one of those scientific instruments, right? A piece of balloon, I'm big on balloons, stretched across it. It's like your eardrum, right? No. And then the other end, what's in it?
metal. A hole.
A little hole. Okay, let's try something. Candle.
Mm-hmm.
So, when I take this and I go,
It's wicked light.
huh?
It's low.
What happened?
It's low.
What's low?
The sound.
What's the candle?
Oh, because the air is
Does
coming
it
out.
move?
The air is coming out of the
Yeah,
hole.
I'm doing a,
The air is coming out of the hole, making.
okay, now then, what I want you to do, you get to do the fun part, right? I want you to yell at this can, right in there. Get down there and yell.
Ooh.
Do it again. Do it again. Do it,
Yeah,
and you
yeah.
tell me what happened.
Ooh.
It moves. The candle moves.
All right, try it
Do
again.
louder.
Do it louder, 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 louder.
Hello.
Come on.
Come on, loud, Caitlin.
Ah!
You're not doing it very loud. Right? Let's see if I can make it.
I'll hold it.
Well, no, we gotta get. The trick is getting the hole lined up with the candle.
No, that's pretty good.
All right, try it again.
Yelling.
Yeah, try again.
Whoa! Did that work?
My grandmother would have loved you. Huh? Did it move?
Yeah, it's it.
Okay.
I
So-
don't see it though.
Every time I do this experiment, it reminds me of my grandmother had gas lights, right? And you light the gas on the stove, it doesn't get very bright. So what they have is they have a little piece of cloth called a mantle that they put over the gas light. And when they light the gas, that burns and leaves a white ash, which heats up, right? So the thing that gives you the light is the gas heating up this white ash thing, right, which is very, very, very fragile. And when we were little kids, when we went to visit her, of course, we were all noisy. And guess what happened?
It blew out.
It would break those little mantles, and then she'd have to replace them. And I don't know what that cost. Probably not very much, and she would get mad at us. But, all right, so let's move on to something else. What's this? Do you have any idea what this thing is?
Pitchfork.
It's a pitch. No, it's a pitchfork. That's for pitching hay. Right? Moving hay around.
It looks like a metal
It's a fork, right?
fork
You want to
it.
eat with it?
No.
No.
Because it's only got two thingies on it, right? You couldn't pick up much with it. It's a tuning fork.
Tuning fork.
Tuning fork, right?
That's what it was called.
That's what it's called, not a pitchfork. Tuning fork.
I was
Pitchfork.
close.
Pitchfork, right? I know you're a farm girl, right? That's why you know about pitchforks.
Oh,
What? What's the matter?
it's loud.
You can hear it vibrating.
You can hear it vibrating. It's vibrating, and I tapped it like that. It's vibrating back and forth, and it's squeezing the air together, expanding the air, squeezing the air together, and that causes that sound wave to travel through the air. Right?
That's annoying.
It's annoying. No,
it's not
it's beautiful.
It's not
Annoying
stopping.
sound.
Still going?
Yeah.
You killed it. Why did it stop when you grabbed it?
Because I
It's
stopped
just-
it from vibrating.
You
it's
stopped
just
it from
vibration.
vibrating. Okay. So, now, camera couldn't see it vibrating, right?
No.
Could you see it vibrating?
I could feel it.
You could feel
Yeah,
it?
I could hear it.
Huh?
Yeah, I can feel it.
All right, let's just prove to the rest of the world. Now that we know that it's vibrating, let's prove to the rest of the world that it's vibrating. I'll take a little cup here.
With dirty water.
Nice, clean water, right?
Dirty water.
It's not dirty water, it's clean water, right? And what we're going to do is we're going to make a mess.
Yay. Oh my god.
Ah,
What happened?
that's cool.
The water started moving.
Yeah.
Water started moving?
It started vibrating the water. Do it two at a time.
Yeah, do the small one.
You can't touch the side of the cup. I knew you were going to do that. That's why I brought a plastic cup. If we'd had a glass one, all right, you probably would have
this one.
broke it. Okay. If you do this up in the science lab and you use the glass beakers, you got to be careful, right? Because if you don't, and you touch the side of the beaker, you're going to break the beaker with the vibrations. Right? Now, we could use that, right, to clean things. If you want to clean your jewelry and stuff, one of the things that they do, right, is they have an ultrasonic cleaner, right? And it goes in and the sound vibrations, right, causes the cleaning fluid in there to vibrate back and forth, and it does a real good job on cleaning your rings and that sort of thing. And they use ultrasonic cleaners for all kinds of things. If you want to get your ring cleaned, take it to the jeweler, and he'll have a little ultrasonic cleaner, right, which vibrates the fluid like that, and we get causes the dirt all to come loose. Now, sound waves traveling through the air, do they get there instantly?
No,
Why not?
because they're bouncing off the walls and stuff.
Okay, but why doesn't that all happen just instantly? Why does that take some time?
I don't know. Why does it take some time?
You don't know why it takes some time? Well, because sound has a speed, right? And the speed varies a little bit depending on where we're at and what the temperature is, right? And how dense the air is and so forth. But it travels at about 344 meters per second,
Wow.
right? Or about 1,100 miles an hour, right? Right?
Cool.
So that it doesn't go instantly. It doesn't get there. So if I get further and further and further away from you, right, then it takes longer for the sound to get to you than it does when I'm standing right next to you. All right, the other thing that happens, you go out in the schoolyard and you yell at the building, which I know you all do, right? Everybody goes out there and yells at the building. What happens? What happens? The sound wave The sound wave travels over and hits the building, goes at
Comes back to
344,
Echo.
and it bounces off the building and comes back, and you get a what?
Echo.
An echo, all right? And the reason that you get that echo is because, right, it takes some amount of time for it to get there and some amount of time for it to get back. If you get back further and further and further away from the building, it's going to take longer for it to get there and longer for it to get back. Right? And you're going to have more of an echo. Right. So, now, I have an instrument over here, very scientific gadget. And what we're going to do is, we said something about sound waves having wavelength. They have a length, right? And what we're going to do is we're going to measure the length of a sound wave with this. This is called a resonant column. Right? And if I take this container and I raise it up, what's happening down here?
That's going up.
That's going up. What happens to this column of air as it goes up?
The air's going out. Because there's no over.
It's all right, but this is getting shorter, right?
Oh.
Yeah.
Right? So we take it
And
all.
that's getting shorter.
And then, yeah, right, because this
It's
fluid,
draining.
this colored water that I have, is draining down through and going into here, right, through this tube. If I lower this, what's going to happen?
It goes
Don't
down.
squeeze it.
It goes down.
It's going to go down. Right now, just like
Sorry.
just like the echo, right? When you go yell at the building out there, right? It goes down and it bounces off and comes back, right? If it were to come back just at the right time, it would make your voice louder, right? Make it sound louder, right? Same thing here is what's going to happen is we're going to get an echo, right? And this is going to go down. If we put the sound up here, we take one of these tuning forks, all right, and we put it up here like this. The sound from the tuning fork is going to go down the tube, hit the water, and bounce back, right? And now if we can adjust the column of water, right, we can get it so that it comes bouncing back, and it's going to make it sound louder because it's going to reinforce the sound. Right? So, now, and when that happens, when it reinforces the sound and it gets louder, this distance from here down to here is a quarter of a wavelength, right? So if at one frequency, it'll be, maybe this is the quarter wavelength, another one down, and the quarter wavelength is what? 1/4 of a wavelength, right? So we get down here and, right, what's happening to that quarter of a wavelength? And if it bounces off right here.
It's good.
It's longer, right?
Yeah, it's longer.
Because look, this scale over here, what's the scale read?
1, 2, 3.
Okay, but what is it? It's centimeters, right? That's 0. This is 10 centimeters.
20.
20.
30.
Right? What's this right here? Where my finger is? What is it right here?
10, 12 and a half.
12 and a half?
No.
Yeah.
Wait, 12,
And a half.
13, 14, 15, 16.
No, the 16's right here.
Okay, it's 12 and a half, right?
Oh, 12 and a half.
All right, what is it up here?
8.
What is it here?
7.
What is it here?
4 and a half.
4 and a half. Okay. You get to read the scale, right? And now what we want you to do is we want you to strike this, all right? Just one time,
Fun part.
right? And we want you to hold it right over the top, right there. Don't touch anything with it, just right over the top, right? And
What do I get to do? I just get to read it?
you get to read it when it gets
Okay.
loud, right? So what I'm going to move, try to move around. Hold on a second. Let me get around through the center. See if I can move around here. Because I'm going to operate this part.
He gets the fun part.
I get the fun part. You get to do all the work.
Okay.
Now?
Go ahead.
Hold on.
Listen up.
It's coming back.
Stop. Oh,
How's it gonna?
what happened?
It's come back.
Now it's gone.
No, it's gone.
It's coming back.
Come back. It's going and it's coming. Everything's sticking
Right.
through.
Did it come back up again? Maybe it's sort of died. Hit it again.
Hold on, I'm getting tired.
You're getting tired. There, it got louder, right?
Yeah.
Right, because the sound waves are coming down, hitting the column of water, and bouncing back up and reinforcing the sound coming from the tuning fork. Right, what is the reading right there?
15.
About 15?
15 and a half.
15 and a half? All right, let's do a little math now. So that's 15 and a half centimeters, and that is what?
What's what?
Hmm?
What's what?
That's a quarter wavelength,
Oh.
right? So what I want you to do,
Turn my arm down, please.
Yeah, go ahead. Okay.
so we're setting it 15 and a half centimeters. Right? And we want to figure out what the frequency is now. So if 15 and a half centimeters is a quarter wavelength, what's a full wavelength?
15 times 4.
15 and a half times 4 is what?
It's not on. Times 4.
61.6.
61.6?
Yeah.
All right, so if it's 61.6, that's the length of a full wavelength of that sound that we were generating, right? Now, here's the formula. What's the formula for finding the frequency?
Speed in centimeters per second. Wavelength over wavelength in centimeters.
All right, now what was this? Yeah, no, you don't remember. What was the speed of sound?
14 point.
It was 344 meters per second, which is how many centimeters? Each meter has what? 100 centimeters,
100
right?
centimeters.
So that's 34,000 centimeters per second is the speed of sound, right? And the wavelength we said was what? 61.6.
61.6.
Right, so if we take 61.6
divided.
and divide it into 34,400, what do you
Big
get?
one goes first.
Hmm? What do you get?
Wait. 34400 divided by
61.
61.6 equals 0.
0 point what?
Zero.
No.
That's the other way around.
It's the other way around. 34,400.
That's what I put in. 34,400
Okay, divided by
divided by
61.6.
61.6 equals 50.
What is it?
558.
558.4415. 558.4
4.
cycles per second. That's the frequency. Or 558.4. Another name for it is hertz.
Hertz.
But it's cycles per second. 1 hertz is equal to 1 cycle per second. Now then, let's see how good we did. Right? Now, of course, the speed of sound in here may be a little bit different. It may not be exactly 34,400 centimeters per second. It may be off a little bit because of the temperature in the room, in the humidity and so forth. Right? And plus the fact, how many times should we do this to check it, to make sure that we,
A lot.
like 3 or 4 times, right? Because
Yeah.
she may have read it wrong, right, the first time. There'll be a little error in reading it. But 558.4, right, now how do I know what frequency this thing is?
Does
Does it say it on it?
It says it on it, right? What is it?
512.
So 512, this is 512 cycles, or 512 hertz per second is the frequency,
Yeah.
and we calculated it to 558.4.
8.4.
If we did it again, right, we might get a little bit closer. If we did it 3 or 4 times and then took the average, we would probably come out to pretty close. Okay. Want to do another one?
Yeah.
Yeah.
Time for another one? Okay, let's try this one.
Fun part. I want to do the fun part.
Well, let's do this one here. This one's probably better.
died.
I think it's 14.
I think it died.
You think it died?
Me too.
What frequency is that one anyway? Let's cheat.
256.
256? All right. So,
Which is 33.6
all right.
wave.
All right, let's try it again. Let's try it again.
So it should be.
Where should it be?
33.6, right here.
Right there? It should be 30. Well, we hadn't gone far enough. All right. Strike the tuning fork.
It died again.
All right, let's try it again. You say 33, 33.6, 34 is right about there somewhere? Okay, let's try it again.
Wow, I can see it vibrating.
There we go.
Yeah. Around 32.
32? Right about there?
Yeah.
32? Okay, so it's 32.
No, it's 33.
So that's 32, and that's a quarter wavelength now.
So,
Right? So it's the whole wavelength is what? 32 times 4, right?
128.
Which is what?
120.
120?
128.
128. All right, so the wavelength is 128. All right, and the speed of sound, we're still going to use 34,400. And to find the frequency, we're going to divide 34,400 by 128.
Divided by what? 128.
Mm-hmm. And what do you get?
268.
And what do you get there?
256.
256, all right.
They
So
were
we're
close.
off again a little bit. We have to do it 3 or 4 times and take the
That was
average.
close.
All right, so we're going back and taking a look at what we're doing. Sound is what? What is sound anyway? It's
Vibration and bouncing off. things.
Vibration.
And then
It's-
coming back
it's-
into your
it's a
eardrum.
wave going through the air. It's
Waves.
Bouncing off things.
compressing the air
Waves.
and expanding the air, right? Compressing and expanding it. And how often that happens is called the frequency, which is sometimes measured in hertz or cycles per second, right? And the higher the frequency, the higher the pitch, right? Remember, if it's like this, it's a high pitch. If it's like this, it's a low pitch, right? The amplitude is how loud it is, right? And if you get real high amplitude, like a lawnmower running, or a jet engine, or the stereo turned up too loud, what it's going to do is really going to put a lot of energy into your ears, and it's going to cause some damage, right, and ruin your hearing. Right? So you don't want to expose yourself to too loud of noises. If you notice the guys that are working around the airplanes down at Logan Airport, they have these earmuff things
Yeah.
on, right? And that's ear protection. Because if they stood out there all the time without that ear
It would be
protection,
done.
they would be deaf, right? So the same thing, if you're going to listen to a real loud stereo, what you should have is a pair of those earmuffs, all right, to cut out the sound so you can't hear it, all right, because it's going to hurt your ears. And so our little resonant column we had over there, we used to measure the wavelength in every quarter, every odd quarter, like 1 quarter, third quarter, we get like an echo coming off of that column of water, bouncing back, which is going to reinforce the sound, and we can use that to measure the frequency of a particular tuning fork. Right, so that's it for today. Everybody, welcome back next time for more fun with science, technology, and engineering.